let me check the sound quality first. Yes, so sound quality is okay. Yo, so welcome you all, and now the rain has also begin with this talk. So for today's agenda, so today I'm not going to deliver that any theoretical talk, and this is that a special session for all participants from batch 1 to batch 5. So that batch 5 people will face some issue to understand because some terminology, some tools that they are still have to learn. So after some classes you have to rewatch this session and you will enjoy this one. So today in this session I am going to discuss about that charge density difference. So generally this is for the interfacing type phenomena, interfacing behavior, one can say. Many questions I generally received from different participants regarding this, especially when someone is working on that sensing behavior or that interfacing of two layers, and we want to uh, calculate this charge density difference. Then what we will do? Charge density difference. Generally in the sensing behavior, what we generally perform, that we take that host material. This is our host, either in form of bulk material. Let me This is that host, and then this is that molecule. So what we generally do, this is the host material, so we can uh, either use DOS, PDOS after optimization of this host, and also we optimize this molecule separately, and then we linked this with, and this system we optimized. So this is that complete system with this host and this molecule. That is a complete system, and with this complete system again we uh, observe this DOS and PDOS, and if there is some change in these two, then we can say that this is showing some sensing type behavior. So this is one method. Second, we generally calculate that IV curve. So IV curve for this host especially, and then this IV curve for this composite. If both are identical, if in the same line it is following, then there is no sensing type effect, and if there is some change in this curve in a negative and positive bias, then we can say yes, it has the sensing behavior. So it's some paper, especially for that sensors where that molecule, gas molecules, or that whatever that biomolecule, it is attached with or connected with or interacted with that host material, and that host material may be nano ribbons, nanotubes, or whatever that nanomaterials you want to use, also in form of that polymers also. So if that type of sensing behavior is observed, then generally we ask that one, uh, what is the effect of that interaction of that molecules with that host. So there are some that chemistry people can study that chemical analysis and a different chemical reactivity, that term we generally, that chemical reactivity uh, in generally we calculate, and we can say yes that this is giving that electron, it is interacting with that electrons, or there is some orbital overlapping type of things are there. So these are that chemical terms. Second, but as far as that physics person is concerned, we observe that the distribution of electrons in that interface. So that distribution of electrons in that interface, it is one way is to calculate this charge density of complete host, and the second way is that transfer of charge from this host to that molecules or molecule to that host. So that is actually calculated on this form of this charge density difference in separate paper. This is represented as CDD, charge density difference. So let us have some paper. So what we will do, first of all, what we will do, we will use a formula for CDD is the formula. So the charge density difference, it is equivalent to this charge of that composite minus charge, and that charge density of this charge density of host minus this charge density of molecule. So this is that method. So this is our host, this is the molecule, and this complete, this is our composite. So we will calculate the charge density of composite, and we will just subtract that charge density of host and charge density of molecules, and that difference is known as charge density difference. So when you search this CDD or charge density difference in Google or YouTube, then there is one lecture is there where some person has calculated this charge density difference by using Vesta. Vesta is the tool to visualize this Vesta. So that is that. So this Vesta is being used, and what he performed generally, he has calculated, he has taken this the Q file of this system. This Q file, do you, if you have plotted this charge density, then you are familiar with this Q file, and for that new participant, this Q file is new, but this is that Gaussian Q file. So he has taken this Q file of this composite, and then this Q file of this host, and this Q file of this molecule, and subtracted using this Vista tool, and created that beautiful image by showing that there is a the accumulation of positive ions are here and accumulation of negative charges are here, and if that accumulation actually shows that charge density difference. So let us see some papers similar to that. I want to show. So I have I was trying to observe some paper on this CDT, charge density difference. Yeah, this one is. So here, let me check. So this is one paper where this ammonium copper carbon dioxide, monoxide, and dioxide, NO2. These are being attached with this is that GGA type studies. So here this is that GGA type studies, and so in this, yeah, so this is that that nano ribbons are here, and in this nano ribbons, these are that molecules which have been uh, used to, which is used to interact with this nano ribbon, and here I think he has tried to calculate this this energy is calculated, that absorption energy is calculated, and that formula is simple. So that energy of that composite minus energy of the host and that molecule, so that the difference is known as absorption energy. If it is negative, means it's good absorption. Magnetic moment is calculated, and this is that Q is, I think, the charge transfer, it's border charge transfer. So the different thing this is. And here this plot is that electron localized function, and this is that charge density difference is here. So this one, charge density difference plot. So this part is the charge density difference plot. And here one that this color, this is for positive and negative, I think, or positive, whatever that. So this is positive. So that distribution of different charges one can see, and how it is interacting with interacted with that. We can any explanation we can use that this figure also. So this is one paper where this charge density difference is calculated. Although that method in detail, it's missing in many papers. Only that data is given, and they have given some reference. So that one. So if you want to include this type of analysis on your paper, then you should also know about the method to get. Let me open that second one. So this is charge difference calculation with this. This is that interfacing type behavior. Yeah, this one. So we can calculate this interfacing type behavior, and here again this is one WASP package is used to study, and bulk calculation, interface calculation is here, and that staking and other things are used different, and that this is the one special code is used, that is ODCA code for charge density difference, and the mechanism is this. This is that formula what I was just giving mathematically. So this is that CDD is equivalent to that rho initial minus this for oxide, and this is for FeBCC. This is for atomic one, and this is for oxide, and this is that into total one. So one can calculate that charge density difference of that interface by using the same formula, and this is that black and white plot for that CDD. This is in the form of contour, so that's why this is looking like this, and black and white pictures are there, so it's not so clear, but one can use that charge density difference to give impact on your paper for the discussion session. One more, I think, try to show you metal oxide. Let me check this. Randomly I have searched some time earlier, and observed some behavior. So this is that yeah, this one. This is that plot. This is the plot, charge density difference. So we can get this plot, charge density difference, and here that material are taken as NIBDC, and this is that composite. So whatever that charge density difference, it is shown here. And I will share these papers to you for how this will help you to explain that behavior, and all these additional study, that is oh, this is yeah, this one, this charge density difference, but unfortunately this paper is in some other language, and I have seen this images, I think so. I think this should be in English. No. Anyway, so that's in the other language. So let me first delete this from my database, because I cannot understand this one. So yeah, this one. Anyway, so this is that the term, and one should calculate this charge density difference for, especially when you are studying that interfacing of that electrode with electrolyte, that battery pupil, supercapacitor pupil, can use that charge density difference. And also if you want to learn that transistor type behavior, there that electrodes are there and that scattering region are there in between, then you should know that effect of that charge density difference in the interfacing with the left electrode as well as at the right electrode. If you are working on that sensing of material, so there is one planar type planar structure material, and you want to uh, have you're just putting that molecules or atoms of the gases or biomolecules, and then you can uh, calculate this charge density difference, and just make your paper easy for publication when you're giving such type of that additional data for that. Anyway, so the question is how we can gauge this. That one simple method I have uh, given, that the charge density difference, if you're having that host molecule and then that composite. Yes. So what we will do, methodology is simple. What we will do, we will calculate the charge density of this, charge density of this, charge density of this, and the formula we will use, this CDD, it is equal to this charge density of composite minus charge density of host minus this charge density of molecule. This is that the fundamental formula we will use. And for DFT, in the case of that DFT, when we will use this term with using this Vesta tool, then what we will do, we will run this uh, that optimize this one. Method will be, we will optimize this, and then we will interact this and get composite, and we will optimize this and get these results. So we will generate that Q file here and that Q file here and this Q file here, and we will use this Q files in this Vista tool and get that result. So let's proceed for the shame. So that the material I have taken for this is I think in this paper, yeah. So this is my system. So here what I have done is I have taken this as this is that host material, and especially this is PBAS, the planar structure material. So what I did, I have created this FDF file, and uh, this FDF file is optimized, and after optimizing I have these type of different parameters in on my hand, and here this is that FDF file, and you are familiar with this FDF file. So it is containing 32 atoms with these are some parameters related to other studies, and then I have optimized and that relaxed one, and I get that charge density parameter, and that is this row. Where is that row file? Here, this is that row file. And then the second one is then I have also optimized this. This is water molecule, and then this is the composite one, where this this water molecule is in interaction with, I think this is not in optimized state. This one is what is that system level here? Yeah, so this one is that optimized state. Yeah, so this is that optimized one. So that was that initial file, and this is that optimized one. So here this is that molecule interacting with this, and again this is also, we will have also that Q file. So one question is, let me proceed step by step. For the interaction of this molecule or atom, that water molecule, I have used that AAC GUI. So what I will do, I generally created that file. So here, although I have given this methodology earlier in any tutorial, how to interact that molecule with that planar structure, so I am using this ASEGUI, and this is one Python based tool. And how to install this, that I have discussed earlier in the different batches, and also for the fifth batch I will give this one. So ASEGUI, this is one Python based tool. So let me open this. So this is that tool, wonderful tool, and let me open that xyz file here. So that one is, this is that xyz file. This, so this is that xyz file of PBAS, and let me view in form of bonds. So this is that in the form of bonds, and they have different utilities to view. So at a different direction change view, you can have this xyz plane. This is uh, z, and with alter xyz one can have this structure. So alter z, this is the z axis, alter x, this is that x axis view, and this is alter y, so this is that y view. So this is that the different views are here. So here that this plane, this is that z plane, means that z axis is in our direction. So we want to put that water molecule, as I have given in this example, and that water molecules is either that will be at the center or at that top of any atom. So let me select this atom. So here that coordinates of this atom is given. So y and z, x and y coordinate, just forget about that, because that will have, and just go to that z axis here, and it's about 3.782. so note down this z axis parameter for this one. So here let me note down that z axis is 3.782. It's a 3.782 angstrom. So I just want to put that water molecule above of 1 angstrom from this particular point. So in this position, so what I will do, now let me deselect this, and let me go to this edit, and here there is one term that is add atom. So yes, so you can select here, this water molecule is already selected, but we want to add. So even we can get this file from our optimized one. So for example, if I want to select this from our database, then I will select here, and we can go to particular location and get that file, and also we can use this molecule from this database of this one. So here this is that H2O, and I want to give the position at a particular value here. So let me deselect this, and here I should use that coordinate. I'm forgetting about y and z axis, but sorry, x and y axis, because that is a different distribution. But I want to put that water molecules above of 1 angstrom from this planar structure, and especially with this atom. So here that the z coordinate of that atom was equal to 3.782. So I will put here 1 angstrom above, so 4.782. So this is that position, and now let me add this. So I think I have missed something. Wrong interpretation by me. Let me delete this. So this is the method, and somewhere I have made mistakes. Let me delete this. So yes, delete selected atom. Yeah. So you can delete this, and let me again add somewhere here. Yes, yes. So I think that will be in many times I have performed this, and but sometime it creates issue. So let me use that water molecule is here, and here that is 4.782. So this is here. Okay, its position is showing here. Anyway, so I have to check this, and I can shift this to that specific position. So why it's not working? There is some data here. Let's some atom is selected. So here, let me move selected atom, and by using that key, specific key, we can move that in specific position. So this is that method to keep this, and here let me keep near to this. So this is that method to keep this. Anyways, so now this is that system, and I can save this XYZ file. So save here, and let me use this composite.xyz like this. So using that XYZ file, I will use this and optimize that. So for that optimization, one thing I would like to mention here. So I have created that file here, and that was that initial file which I was created. This was that initial file I have created by using ASCII, and by rotating or whatever that things I have performed. So it requires actually a little bit practice. So after creating this, I created one FDF file for that. So this is that FDF file. So here this is that FDF file of that, and water molecule is here, and this bottom this three coordinates, these coordinates are of that water molecule, and starting from 1 to 32, that is that planar structure. And one thing here I would like to mention is just to give, see here. So I keep that planar structure as fixed, because all these that water molecule is optimized as well as that planar structure is optimized. So I don't want to disturb that structure of that planar structure. So I fixed all the atoms of that optimized planar structure. So here I'm using this block, that block geometry constant, and the position from 1 to 32 mean that planar structure, it is fixed now. And then only I am keeping this three atoms or one single molecules of water to free move. So after certain instant, after how many steps of Siesta run, let me show you that result file. So this is that result file, and that relaxed so this is that relaxed file, and here that relaxed configuration, and it's after how many CG steps? It's after 219 CG steps. It has now the fixed position of that optimized system. So this is that output file of the composite of that planar materials with that molecule. So I have three different files. One is that composite, and second one is that planar structure, and the third one is that water molecule. And here one thing I would like to mention is I have taken this block identical for same. So that is this lattice vector, especially for same. This is for composite, and second one, this is for that planar structure. So and also I removed that and this one is for all these that coordinates, especially that lattice coordinates, I have fixed because to avoid that extra errors. So this is that method. Now, so I have now the charge density term, and this charge density is this row. Where is some row file is here. So yeah, this is that charge density file, and for everywhere we have this charge density file, and here also that charge density file. So everywhere this RO file is there. So the step number one is over. First, what I have performed, I have optimized that planar structure by using our method of optimization. and then that I have optimized this water molecule, and then I have linked this water molecule with that planar structure and optimized the complete system. And now I have created that row file for each category, each systems, one composite, second for that host, second one for next one for molecule. And now next I will try to generate that cube file. So the method of generation of that cube file I have mentioned earlier, and that was the use of that G2C underscore, yeah, underscore NC. Let me check this utility I have used earlier. And so first of all, let me show you that utility available in my system, that should be here. And in this util there is one grid this file, and here it is there, but it's not here. Then let me, so I can compile this by using Mac. So this is generally compiled in series version of that. So I will use this ng G2C ng, this command. So in order to use this, I will link this with bin directory sudo G2C underscore this to user local bin, and I will give this CP. I have forgotten. Yeah, so now it has been linked to this. And then the method is, we can have, earlier we have discussed about this during that charge density plot, and one of that lecture available for this charge density plot is so one thing we can create is that cube file by using this tool. So let me go to that this one. So I can create that cube file directly here. So let me open this, and we can directly convert that file by using this. So G2C and help, we can take this. So generally, earlier I have mentioned this method. So G2C, and then x is 1 minus y is 1 minus z is 1, and then minus n is 1. And also then we take that structure file here, minus s is that structure file, and generally that structure file we take is yeah, the structure data out, this one. Okay. That is the structure file, and then we put that what is that file, grid file. So that is represented by Z. The command is here at the top, that is struct file and then grid file, and grid file is our row file. So where is our row file? This is our row file. This is our row file. There is some issue. This command is not working. So let me check again. This, the spacing is here. Okay. Struct data out. Here is also S is there. Yeah. Minus 1 minus z. Y is here. we have taken the right one, but still it's creating issue. Let me check this. The same is the same, otherwise this will not use this. Okay, so again for the next file, let us try to use this command, otherwise we will, let me use here the same command, otherwise I have to recompile that in somewhere. So that is g2c and z minus x1 minus y1 minus z1 minus n1, and then minus s, that is struct file is here, this one, and then minus z, the grid file. Actually many times I have used my computer system for different tutorials, so this type of suddenly I have removed anything, and then yeah, it's working. So this is good for this one. And also, so this will create this cube file. So this is the method of creation of that cube file, and why it's not working for this water molecule, I am surprised. And also we can generate this cube file with this. For the second one, let me open another thing. So this is g2c minus x1 minus y1 minus z1 minus n1 minus s is that struct file, minus g, it's that row file. So here our row file is yeah, this one. Yeah, so this is also creating that grid file. So one thing I would like to share with you, look at these two. Let me check this difference. So this particular utility actually uh, create that grid file, but this grid mesh, it is important. Here this grid mesh is taken, it's a 150, 150 and 80, and it is taken as 150, 150 and 180. So when you use to convert this row file into cube file by using this utility, that grid mesh will be automatically taken by this particular system, particular tool, and this will create some errors when we will use that Vista. So this method of creating a cube file, this is not good to get that charge density difference. So another method to get this file, cube file, is by using that row to XSF one. So that row to XSF file, what we will do? So we will go for that the second utility, that is row to XSF, and this will give our XSF file, and there we can put our grid values as we want. So that selection issue is on our hand. So let me use that one, is that row to XSF. This is another utility, and that new people will uh, really uh, all these are new for that batch 5th, but others are knowing this one. So here this is that system level. So let me open FDF file. I am just repeating whatever we have performed earlier for charge density plot. So there, this is that our system level. Copy this and paste here, and here this will ask for this. So this is angstrom. Now origin we are taking that 0 0 0, yeah, and then we put that is spanning in three different direction. So the first spanning is this, so we take this from our lattice vector. So let me put this and put here. For the second spinning vector we will take this second. So this is our second spinning vector, and that third spinning vector we are having this. Yes, so this now it's already available, so yes. And now here this will ask for that grid point, and here we can give this is 60 60 60, and we will fix this grid point for all three systems, because that mesh grid that must be identical for the charge density difference. So let me use this ROHO, and then this is by. So this has created now that XSF file, but we want to have this XSF file as Q file. So what we will do, we will open this with our Vesta. So Vesta tool is already installed here and on your system also, and that Vesta with this XSF file. So let me open this XSF file here. This paste here. So this is that XSF file or charge density of that planar structure, and here this is in form of XSF. I will export this in form of cube. So let me export this data. So this export this data that will be in form of cube, so I can add this as in form of cube. So what we will do, we will perform that row to XSF for all these three, and then we will open this with Vesta tool, and we will save that data in form of cube. So this is another method to get that cube file for different system. So let us check, these are that method, and I have taken this is for that PSF file, and the second one is this for also that cube file should be available here, because I was earlier trying to get this. So here let's check that cube file is available or not. Not that, and then I will have to generate this. So XSF file is available. Let me check here. Yes, XSF file is available. So let me open this XSF file by using Vesta with this XSF. Yeah, so this is that XSF file with water molecule. This is the charge density plot, and I can save this in form of cube. So export data. So here this is with cube. So let me delete this. Okay, so this will be saved in form of cube. Again, let me go to that water molecule. So this is in the water molecule. Again, I should have this XSF file here. So let me check that XSF file here with Vesta. So Vesta star.xsf. Yeah, this file is here. So this is that XSF file for water molecule, and again I will export this data in form of cube. So this is that mole with cube. So now I have the cube with the same grid pointer as I will have created that row to XSF, created that XSF file by using the same lattice parameters as well as that grid parameters with the same data. Now I am going to calculate this charge density plot and watch carefully what I am trying to do. So first I will import this, then this and this, and with minus sign. So let me open this Vesta with here. So let me here. Yes. Okay, so that cube file is so let me open that Vesta. So open here that cube file should be there. That cube file is generated by that tool, and here we have generated this cube file. Yeah, so this is that cube file generated by us using that XSF file. And now let us edit. So this is for the composite one, and I am going to subtract this by using this edit data. And this data is not the ordinary one, this is volumetric data. So remember this, in the edit data you have to move to this volumetric data, and here we have to, this is that original one. Now we have to import. So import this data, and uh, from where we have to import, from this point, and here that there are two cube, one is that generated from that tool, and there we have converted this. So this one is now opened. Now here that parameters, what do you want to have? Add to current data, subtract from the current data. So we have to subtract in this one. So this is now subtracted. So I think it should work. Yeah. So this is the second one. Yes, this one. So this first one, this is the second one, it's subtraction form. Anyways, and then again we have to subtract the third one. So the third one is that water molecule, this water molecule. Yes. So again we will subtract this and this. Now these are that parent composite. This is for the first one, this is for the second one, and now let us apply. Okay, so this is that data, and whatever that this things we are observing, that is from the nearby supercell. So we can subtract some lattice vectors, and we can get that clear image. So this is that only that additional charge is towards this, so that is showing that interaction with this. So these are one type of this charge, and this one is the one type of charge, and this is that second type of charge. So this is that the plot of charge density distribution and charge density difference, and we can save this in form of we can even that export data in form of that complete charge density in form of cube, CSDIE form of cube, that is for complete one, and we can save here. And also in form of that contours and other things we can create by using that utilities, so that 2D data display and other things, and we will have different slice, and it needs a little bit practice, so we can get that charge density of this one. So this 3D is okay. So many papers this type of plot is showing, and you can have that contour plot and other things at different planes by using this. So you can have, in one paper we have observed that contour plot, so you can create that contour plot also. Anyway, so this is that method of generation of charge density difference, and especially one who is working on that sensing type behavior, one should use this method to get that charge density difference. And this type of output, especially that lower part and other part, that is because of that selection of that lattice parameter. So just avoid that vacuum created, because I have created 10 angstrom vacuum. That's why it has just trying to uh, linked with that neighboring one. So this is looking good, no problem. So method is simply when we have to create that planar structure, especially if for such type of project, we have to optimize that. Then we have to create that molecules, and then optimize. Then we will link this by using this ASA GUI, and after some practice you can put that at a particular position you want, and then fix that planar structure, and release keep open to that molecules, and let it should be optimized. So after optimization you will have three files, one for molecule, second for a host, and third one that composite one. And then you have row files for all these three components, and then you have to create that cube file. So for in order to create that cube files, you have two methods. One is J2C underscore NC tool, and sometimes this NC tool it is not working on that molecules we have observed today. For water molecule is what not, it was not working, but this for that 2D materials it was working. And but that cannot be used, because that cube file generated, it was that grid point was, especially grid mesh was selected by that tool, and that will be different. So that will create the error here in this method of taking that charge density difference. So what we will do, we will first create that XSF file by using row to XSF utility. So row to XSF utility, you will have that XSF file for separate 3 components, and then that XSF file we will open with Vesta and export data in form of Q file, and that Q file we can select here, and the method I have shown first. Open that Q file and then import that that other 2 files with the subtraction of this original one, and that you will get this type of structure. Anyway, so happy learning, and try to do this charge density difference for your system also. All the best. Thank you all.